All right, hey, okay, welcome back here. We are getting started with week number 4. And so I thought I would begin with a little bit of kind of a highlight of where we are and where we're going. And at the end last Wednesday, I said, hey, we're halfway done. And so let's start the second half. But given that we've gone through the weekend now and we only have the second half, you might be surprised to hear this. We only have 2 weeks and 2 days. So watch, looking here at the calendar, we're right here today. We're at June 8th. And so we will do our Monday, Tuesday, Wednesday this week. Next week would be week 5, a Monday, Tuesday, Wednesday. And then finally we'll get into week 6, which is Monday, Tuesday, Wednesday. So we're right here. We only have 2 weeks and 2 days. And sure enough, then we'll have our final exam. And there's a lot to do in that amount of time. As you know, we've been doing a lot of lectures, a lot of labs. We've only really had one test. And now we're ready to keep lecturing, but now the tests come in not at a faster rate, but now that you've already done the learning, so the learning is on the early part of the semester. Now the testing is on the latter part of the semester. And I think you're probably familiar with that. And so I just wanted to start off with a little bit of heads up to say, okay, things are going to go a little bit quicker now in the sense that the tests, which always seem like a pressure place for students. And so next Monday, a week from today, you will have test number 2, because as I said at the beginning, I like to go 2 weeks and then have a test, so we did. And now 2 more weeks we'll have a test. So we've already done one. Now we're about to do a second week and have a test. Then the next 2 weeks we'll have a test, but that's where it gets real busy. You can't go a whole 2 weeks, which would be the following Monday. And so at the end of this 2 weeks, we have test number 3, and then we have a comprehensive final exam on that Wednesday. And so going into next week, week 5, you have one test, and then week 6, you have a test on Tuesday and a final exam on Wednesday. And so just a little bit of heads up. And we'll do the tests and the finals exactly like we did the first test. And so if you have any questions about that, send me an email. I will send you emails kind of explaining and highlighting a little bit more, but I will tell you it won't be anything new. It seemed to go pretty good. There'll be hopefully a few improvements as we get to test 2 and test 3 and the final exam, but other than that, I think it went well. Now, I will say there's one thing that I meant to do this weekend, and I got real busy this weekend. Didn't quite get to it, but I need to make sure I do that. On Canvas, I need to give you a spot to turn in this stuff related to the second third of the class. That is your homeworks 7 and 8. And then also we're going into 11 here today, and also the labs. And I haven't given you a place to turn that in. In fact, I haven't even got a chance to grade your homeworks and labs from the last time. And so let me take a moment to say that the tests are there. They're graded. You've already seen those. But the homeworks and the labs, I haven't actually added score on the grade book for that, but I will soon. And know this, if you've done the homeworks and the labs, you're going to get 100% on those. And so that's those are graded just on effort, not right or wrong like the tests. The tests are graded right or wrong, but the homework is graded on effort, and the labs are graded on effort. So even though it's not recorded, if you've done it, you can have in your mind that you're going to get 100% on that. I just need to double check to make sure you did it, and then I'll give you your 100% here. So that's where I thought I would start today. And so let's continue on in chapter 11. As you know, when we left on Wednesday, we were right here. I left it on the board over the long weekend and said, okay, we were talking about the mass of the atom, and so here is that whole discussion. Let me not repeat it, but let me just say here, let's wrap up chapter 11. I'll say it again. Chapter 11 is our first non-mechanics chapter. It is a long chapter, but not a really hard chapter, but a long chapter. And so I'll come back over here to this periodic table. Let me get my little pointer and say, all right, remember this great periodic table. the periodic table, and let me just pick on, I'll go to helium again. That seemed to be the one that I kept constantly picking on here. But as I was trying to point out here, what we call the atomic number, the number 2, that's really the number of protons. And over here, what we call the atomic weight, which really probably should be called atomic mass, really has 3 meanings, and I showed you 2 of them, and I want to finish up here with the third one. The 2 I showed you, the first one was to say it is the nucleon number. And so for helium, the number 4 up there told us that we had 4 nucleons. And since the atomic number was a 2, which told us it had 2 protons, we knew that there was also then 2 electrons, at least on normal atoms. Then we learned about the word isotope, and the isotope meant that we could have an extra number of electrons, or not an extra number of neutrons, or we can have a lower number of neutrons. And so that's why the number of nucleons on average wasn't an exact integer. But the second meaning of that atomic mass was right here. That if you looked up the number, this is actually then telling you, and there's the helium from last time, the 4.003 AMU. It's just telling you this is the mass of 1 atom of helium. There is a third meaning to that number, and so let's put out the third meaning. And so if I put helium and I say its atomic mass number is 4.003, which, as I said, and I'll just repeat it here, you could think of this as the number of nucleons, or you could think of it as the mass of 1 atom. But it's hard to get 1 atom, and especially back when this periodic table was made, there was no way they could get 1 atom. And so the third meaning of it is a grouping of atoms. We like to group things because sometimes 1 is just not enough. Here's what I mean by that. Probably, no, I was going to say not never, but sometimes you do go to the store and you buy 1 cookie. I know sometimes I'll go to Mrs. Fields Cookies because I make those big, really good chocolate chip cookies, and I'll order 1 cookie. And even sometimes I'll order 1 donut. But the truth is, a lot of times I go to the store, and especially for the family, I buy a dozen donuts. I don't ask for 12 donuts. We put it in a group and we say, give me a dozen. Same with the cookies. Give me a dozen cookies, or give me 2 dozens worth of cookies. We group it together. Likewise, you heard me say that already about, well, how much time is left before this summer session gets over? Well, 3 weeks. Well, really, 2 weeks and 2 days. But you see, I'm grouping it in weeks. You know that a week is 7 days. And I could have said, instead of 2 weeks and 2 days, I certainly could have said, oh, it's 16 days. But there's something nice about putting things in a group. And so 2 weeks and 2 days really, of course, means the same as 16 days, but it's just different. It's easier to work with. Somebody may ask, well, how long before Christmas? Well, when you want me to count how many days before Christmas? It's probably easier to say, okay, we're about mid-June. Why don't we just go July, August, September, October, November, December, and then depending if you want to count this month, well, just leave it alone and say 6. There's 6 more months and a little bit that's left. But you see, I'm grouping it in months, and so we have a tendency to do that. We can say thousands of people, and so we put them in groups of thousands. Maybe a less common word is a score, a score of people, or Abraham Lincoln, at the Gettysburg Address. 407 years ago, our founding fathers. Well, what is 407 years? Well, a score not as common, is 20. So 4 score would be 80, and then 7, so it would be 87 years. And so certainly Abraham Lincoln could have said 87 years, but he didn't. And we do this a lot. Why do I say that? Because the third meaning of this word is to say, let's put it in a group. And if you put it in a group, the 4.003 is the mass in grams of this grouping. And so maybe I'll say this is the mass per, and if you let me start off, I'll just say per group. How much of a group? Well, this idea was put together by a guy named Avogadro. For us in California, we like to call it avocado, it's number. But Avogadro's number here is then this group. And so this group is referred to as a mole. And Avogadro's number then is often then the way to phrase a mole. And so the last example I gave you with a score is purposely because you may not be as familiar with a score, but I think you're familiar with a week. And so notice that, saying 2 weeks and 2 days is a lot like saying 407 years ago, and it's a lot like saying, let's put this in a group. How much grams would it weigh if it was in a group? Not a group of 7 like a week, not a group of 12 like a dozen, not a group of 20 like a score, but in a group of a mole. And a mole is chosen because it is an enormously large number. It takes a lot of atoms. As we come back over to here, you will see that one atom has very little mass. So clearly, in order to get to things that are measurable in grams, you're going to have a lot. And so let me put here then, this is a big number. And for those of you who haven't seen Avogadro's number or a mole is 6.02 times 10 to the 23. And so it is a grouping far bigger than a score or even a year. You might say, how long before I finish my college education? And you might say, 4 years. Okay, well, you see, you're grouping all these days in a year. You know that there's 365 days in a year, but you've grouped it together so it just is a 4 year. You didn't have to multiply out 4 times 365 and say some giant number and, what is that, like 144,000 days here, or 4,400 days, so 14,000 days. You're like, no, I don't want to say it that way. What I want to say then is just this is what its mass is in 1 mole. And even though it's a huge number, fortunately these atoms are kind of small. It's why I brought these out here. These are what we call our mole samples, because these have been manufactured to be exactly 1 mole. And so this right here is 1 mole of aluminum. And so this many atoms, that's 6.02 times 10 to the 23rd of these aluminum atoms make 1 mole. Here's 1 mole of copper. Copper, again, they pull themselves in a little tighter. So volume-wise, it's not even the same, but number-wise. Here's 10. I think 10's kind of somewhere in between them. Yeah. And then here is iron. And I think iron and copper, about the same there. But all of those are designed to be 1 mole. And so, again, this is kind of our grouping. But you can see we like this group because this is a big enough that it's workable. and so we like to group it, just like grouping time in weeks. It's something manageable. Okay, we could say summer school is 6 weeks. We could say a regular semester, this fall semester is 15 weeks. It's a good grouping, something to work with. And so a mole is a good grouping. And so I'll just say it one last time, but maybe I'll then pick on aluminum here. So I could say this: if I had 1 mole of aluminum, how much would it weigh? Well, that's where the periodic table comes in. So when you jump over here, you could say, okay, let's go over to aluminum. All right, here's aluminum. And so if I look at this number, this 26.9, I'll just do 2 decimals, 98, and I look at that number. Now remember, that number really has 3 meanings to me. One of the meanings, I could round it to 27 and tell myself, hey, there are 27 nucleons, which since there are 13 protons, there must be 14 neutrons. So that's one way to handle this number. And of course, the other way is I could say it's 26.98. That is the mass of 1 aluminum atom if I'm in atomic mass units. But the third way, what I'm trying to show you now, is I could come over here and say then that aluminum has a mass of 26.98 grams in 1 mole. And so if I told you I had 1 mole of aluminum, I then would be telling you that that number that I read on the chart is its mass in grams. So as you do the homework for this chapter, you will see a question like this. Maybe the question will say, you have, and I'll start with the easier of the two. You have, let's say, 2 times 10 to the 25th atoms. 2 times 10 to the 25th atoms of aluminum. How much does it weigh? Okay, well, again, I hope what you're getting at is our first step is really to say, let's put them in groups of a mole. And I think because the word mole is new to a lot of people at this stage, this is why students in a face-to-face setting, and I'm sure you guys too, always have a hard time with this word mole. You might even come across chemistry, and students for some reason just have a hard time with it in chemistry. And it's really not supposed to be that hard. It's like putting things in a group. It would be like me telling you, if I had 36 donuts, well, how many do I have if I were to say, how many dozen donuts do I have, right? You would say, well, 36 donuts, you would divide it by 12 because that's your group. Exactly. And of course, you would get 3 dozen. So I'm going to do the same thing. I'm going to come over here and take my 2 times 10 to the 25, and I'm going to divide it by 6.02 times 10 to the 23rd. That's my group. This is telling me how many atoms fit in the group. Now the group is, of course, a mole. So this would be 2 times 10 to the 25. And then I would divide it by 6.02 times 10 to the 23. And this would tell me then that I have 33.2 moles. Now maybe the units could be helpful here, because remember up here in the numerator, this is the number of atoms. And remember this down here is the number of atoms per mole. And so if you write this as a compound fraction, and I'll just put it over here and say, okay, in the numerator I have atoms over 1. And in the bottom, I will flip and multiply, so this will make mole over atom. Atoms cancel off, and you're left with moles. Sure. So looking at unit analysis, it works great. But again, even without unit analysis, if I would have told you 14 days from now, we're going to be starting our last week, you would have go, oh, 14 days, that's 2 weeks. Because you would have gone 14 divided by 7, right? You would have put them in a group of 7. And that's my first step here, is to put it in a group. How many moles do I have? Okay, so I start off with how many atoms, and from them I have a certain number of moles. And the reason I want to put it in the number of moles is because, again, here's what I know. I know what the mass is for 1 mole. And so if I come to my 33.2 moles, and then point out here that my mass is 26.98 grams per mole. Again, you can kind of see that. Again, maybe a good analogy would be to say, if I told you, you had 14 donuts, and you wanted to know how much it was going to cost to get these 14 donuts, the first thing you would do is probably take the 14 donuts. I'm sorry. Let me make it easier number. I was still thinking weeks. How about we go 24 donuts? So if I take 24 donuts, first thing I probably would do is divide it by 12, because that would tell me how many dozen I have. Okay, so I have 2 dozen. And then if I know it's $10 for a dozen, then I would go 10 times the 2, and I would get 20. So those are your 2 steps. The first step is to, figure out how many dozens you have. And now knowing how much it costs per dozen, you can multiply that. And that's all I'm doing. I'm starting off with a bunch of atoms. From there, I can figure out how many moles I have. After that, I can figure out then how much mass I have. Now, I'm going to need a calculator for this number. And so I have my 32.22 still in my calculator. So I'll multiply it by 26.98. And I have then 896 grams. The moles will cancel off. And so I've answered this important question. How much mass is 2 times 10 to the 25 atoms of aluminum? Okay? Let me ask this same question in reverse. What if I were to tell you this? What if I were to tell you I have a piece of aluminum right here? And this piece of aluminum is 500 grams. How many atoms are in it? And if I continue with my analogy of the donuts, costing $10 per dozen and having 24, this would be like saying, okay, I have $20 to spend on donuts. How many can I get? And so the first thing do is to start out, okay, well, what's the total I have? In that case, $20. And from that would tell me how many dozens, how many groupings I can get. Once I figure out how many groupings I can get, I can then figure out what the total individual number is by knowing that there are 12 donuts in a dozen. And so I'm really going to do the same thing. And so there's nothing fancy here with the word mole or Avogadro's number, other than it may be a little new to you. And so I'm trying to convince you to think of Avogadro's number and a mole in the same way you would think of a week and a dozen. It's just a way of grouping things together. And it's convenient. So here I begin. So I'm going to go ahead and say, all right, so if I were to tell you that I have 500 grams of aluminum, and then the question is, how many atoms do I have? Just like the 24 donuts, just like the $20, I would want to know then, with the $20 would get me, how many dozens would that give me? In that case, it would give me 2 dozen. So in this case, I'd say, how many moles is this? And so here's the 500 grams. And anytime you're trying to figure out how many grouping, right, that's a division. Division is always how many of these fit into those, right? That's why we learned division back in 4th grade. It was like how many of these little things fit into the big thing. So having 500 grams, I would say if I were to divide that by 26.98 grams per mole, this is really saying how much of this fits into here. This is going to tell me how many groupings I have, how many moles do I have. And then once I have the number of moles, then I can easily get to the total number. Just like once I know the number of dozens of donuts I have, I can get to the total number of donuts. So grabbing my calculator and taking 500 and dividing it by 26.98, I will get 18.53. And it should be moles. Let's check our unit analysis. We will go ahead and I'll just write grams over 1 for this numerator and then flip it and get moles over grams. And so grams cancel off, and sure enough, I get my number of moles. And so again, taking you all the way back to chapter 1, don't overlook the power of unit analysis. We're going to divide the two. That's what our logic tells us we should do. That's what our fourth grade division is telling us to do. But if our logic is correct, our unit should work out right. And so this should tell us how many moles, so do the units come out that way? And they do. And so that gives me some confidence. I know if it didn't come out to be moles, I had done something wrong. And I'll say it again, just because it does come out to be moles doesn't necessarily mean I did it right. But it does seem to indicate that I'm doing things right. Okay, so this is halfway there. Just like if I started with $20, knowing that a dozen donuts is $10, I have concluded that I can buy 2 dozen donuts. So what I've concluded is this chunk of aluminum, that's 500 grams, represents 18.53 moles. And so once I know that, just like knowing that I have 2 dozen donuts, I can then multiply how many are in the group to figure out what the total is. So here I go. I'm going to take my 18.53 moles and then multiply, and I'll say it again. Maybe I've carried this analogy a little too far, but if you ever find yourself struggling with these, I think it's just more because moles and Avogadro's number is new to you. Or semi-new, because you might have seen it in chemistry. It is pretty common to see it in a high school chemistry. Just think of these as donuts and dozens, or for you healthier people, bagels, whatever. But they come in these groups of 12. And so I know if I had, 18 dozen donuts, if I wanted to know how many donuts, since a dozen is 12, I would just multiply by that grouping of 12. And so that's my clue. I know I have 18.53 moles, so I just want to multiply by the grouping, and the grouping is a mole. There is 6.02 times 10 to the 23rd atoms in 1 mole. And so then grabbing my calculator, the 18.53 is already in here. So 6.02 times 10 to the 23rd would then tell me that I have 1.1, I'll just round it to a 2, round it up, times 10 to the 25 atoms. And that kind of makes sense. Because if we go back to the problem we did earlier, 2 times 10 to the 25 came out to be somewhere close to 900 grams. So half of that would be 450 grams. And so 1 times 10 to the 25 would be 450 grams. And so 1 times 10 to the 25 would be 450. So this extra little bit more than 1 is the part that makes us go a little bit more than 450 grams. And so it gets it up to a 500. So as I think about what the numbers mean to me, it begins to all kind of fit together and make sense. Well, to be quite honest, that's the place I was at least hoping to get to when we ended on Wednesday. I knew we wouldn't actually finish the whole chapter on Wednesday, but even though that's the schedule, because I know it's a long one. But let me call this maybe halfway done with the chapter, maybe more than halfway. But let's continue on, because your author, still talking about the structure of matter, shifts a little bit, and he gets away from the direct structure of it and the periodic table, and really what I will call the consequences of all of this. And let's begin with what we call the ideal gas model. It leads to the ideal gas equation. And as the name implies, maybe I should call this the gas law, because that's also another common phrase. But the ideal gas model is the following. It's saying, okay, now that we've just done the structure of matter, and we looked at this periodic table, and let me just pick a gas, how about in the air here, of nitrogen. That's the most common. About 80% of it is nitrogen. Let me get my pointer. And so there's a lot we could say just from the periodic table. And so here's the N for nitrogen. And so these atoms are in this room. Now I should probably be a little careful. Beyond the scope of this class, there's a little bit of knowledge of chemistry I would have to point out. Nitrogen loves to hook up with other nitrogen. And so floating around in this room right now is a lot of what we would call N2. We put a little subscript 2 because a nitrogen would hook up with a nitrogen. If I made a picture of this right over here, it would look like this. The nitrogen would hook with another nitrogen, and they love to grab each other. And in fact, it's kind of like they got 3 hands each, or 3 hooks each, and so they come along and they have what we call a triple bond. But again, all that's really not the point of this class, and so you'll study that a little more in your chemistry, and maybe you already have. But here's what I want you to see. What we call the ideal gas model, then, is in this room we have floating around mostly nitrogen. And the nitrogen, as I said, is hooked to another nitrogen, making a nitrogen molecule. And so I've got billions and billions and billions of these. Maybe I should say moles and moles and moles of these floating around the room. But we could think of them as individual objects, like maybe little tiny ball bearings, if you will, and they bounce off each other as they move around. So in other words, they don't hook to each other. And that's why I brought this little toy out here. This is what we call our ideal gas model. If I turn it on, and as you saw before, it's kind of loud, so I won't leave it on too much. But we have put in here a bunch of little tiny ball bearings. And these ball bearings bounce around, and they hopefully give you a good visual representation of what we call the ideal gas. And let me just turn that off just in case you can't hear my words over that loud thing. But these bouncing BBs, we like to say, or these ball bearings as they bounce around, are really a good visual picture that I want you to have of these nitrogen ones. And so this is this ideal gas model. We call it idealized because there is a small electrical or chemical interaction between these, but it's really small. And if it's so small we neglect it like we would with ball bearings, the ball bearings then is the ideal model. So our real gases behave almost like an ideal gas. And for us, being our intro to physics here, let's not talk so much about a real gas as much as an ideal gas. Let's start there. And if we can understand an ideal gas, then later on in your education, you'll be ready to make the next step and say, okay, well, what if there is some interaction? So let me come back to my picture and then just erase these. And so my ideal gas is to say there is no interaction between them. And like I said, so real gas, there is going to be a little bit. But fortunately, for most gases, and particularly nitrogen here in this room, the interaction is so small that the physical results of what we get with a real gas are really very, very close to what we get when we have this ideal gas. Okay, so with that in mind, I'm hoping you always have that mental picture when it comes to dealing with a gas of these BBs bouncing around. And so I'm not going to put it in words, but I'm just going to draw a little picture here. We have this container then filled with these gases bouncing around. Which, by the way, gives me a little bit to say about today's lab. And so today's lab, which would be lab number 7, and I should have pointed out this is lecture number 9. I should have said that at the beginning. And we will eventually have 16. That's why we're halfway through here. But we've had 8, and we've got 8 more to go. But this one, now I lost count, is number 9. And the lab today we're going to do, lab number 7, is going to be exactly this ideal gas model, and to test this ideal gas equation. And so we're going to have this container with these molecules bouncing around. And I'll show you more of that when we get into the lab. But let's just make sure we have a good understanding then as we go forward here. And so you can see that crazy thing bouncing around. And you can probably see, and I'm just going to put a capital V here for volume, that this gas has a particular volume. It also has, let me put a P for pressure, and let me put a capital T then for the temperature. And so we're talking a little bit about, like, for example, what is the pressure? And so I'll start there. And this is where this